All right, the next section that we have is cylindrical and spherical coordinates, so triple integrals in those coordinate systems. So cylindrical conversion factors are the same as polar, with the exception that in polar there is no z, but in cylindrical there is a z, but z doesn't convert at all. Cylindrical coordinates is literally polar coordinates plus the z direction. So very informally, I think of cylindrical as being equal to polar plus z. That's really all it is. If you can do triple integrals in Cartesian coordinates, really all you're going to do for cylindrical, for integrating, for doing triple integrals in Cartesian coordinates, we will interpret every region as z simple to figure out what our top and bottom surfaces are as ordered in the z direction. And when you project that region down into the xy plane to to do your double integral, you then just choose to interpret that region as radially simple. Much like in polar, we have the little extra factor of r showing up in in our dv, but we have this extra dz here as well because we're now in 3 dimensions. We have 3 variables, dz, dr, and d theta, so we get this extra copy of r showing up, just like we do in polar. So, like I said here, for cylindrically simple regions, you basically will order, you will order your inside integral. So you'll always do z first for cylindrical. Always, always, always this order, z, r, theta, every single time. So identify your top and bottom surface, and you just want to make sure that you convert them into polar. That's why there's an r or cylindrical. So that's why there's an r and theta there. So for example, in the when I was doing the previous video, if you were following along, we had a top surface of z equals 4 minus x squared minus y squared. Well, if we were going to put that here, we'd have to convert this. Well, in cylindrical / polar coordinates, x squared plus y squared is r squared. So since these are each minus, this becomes 4 minus r squared. And the bottom surface we had was z equals x squared plus y squared. So in polar coordinates, this is just r squared. Z equals r squared. So more or less begins the same way. Identify your top and bottom surface solved for z, but then whatever you have here, you just want to make sure that you go ahead and take this over to cylindrical coordinates. Just like in polar, you want to convert your x's and y's to r cosine theta and r sine theta respectively, and you get this extra copy of r along with your differentials. For spherical coordinates, on the other hand, things are definitely different. We still have some ideas of polar coordinates showing up, but it is a little bit more than just polar plus something else. So let's take a little bit more of an in-depth look here for spherical. So for spherical coordinates, we have these equations. These are our spherical conversion factors. Our differential volume is also a bit different. We've got our differentials, and it's always in this order for our integration. Always going to be doing with respect to rho first, with respect to phi, and then lastly, always ending with theta on the outside. So, for these bounds here, the way we're going to think about this is for spherical coordinates, the technical term is a centrally simple region, but we don't have to use that terminology. So let's just go ahead and do a very, very, very standard and typical example, and that is something of like an ice cream cone. So imagine you've got a cone, and then on top of it, maybe we've got a sphere centered right here. So something like that. So a literal ice cream cone. So maybe I should make my z-axis go up a little bit more. There we are. So x, y, and z axes. And let's go ahead and say that this cone has the equation, say the equation of the cone has equation z equals the positive square root of x squared plus y squared. And then this sphere up here, let's say, well, hemisphere, right? Let's say this has equation z equal, or yeah, I guess we could go ahead and I'll just write it. As a full sphere. We can go ahead and say this is x squared plus y squared plus z minus 1 squared equals, let's go ahead and say 1. So this equation does produce the lower half here, but we're only going to talk about the top half of it. So for spherical coordinates, what you want to do is sort of like you did in polar coordinates. You'd start at the origin and imagine striking lines outward through your region. Well, what surface do you hit? Well, the last surface you hit is this equation here. So for us, what we want to do is list what rho is. So rho is the distance from the origin to your surfaces. So what is the equation of this sphere solved for rho? Well, you'd have to convert this equation to spherical coordinates. That's one way to do it. That's true, but it's not the smartest way to do it. Really, you want to think about, well, because this is shifted up, we would actually have to somehow convert this a little bit. So let's go ahead and actually convert this. So using our spherical conversion factors, we can go ahead and figure out, in spherical coordinates, this turns into something special. Rho squared sine squared phi. And for the purpose of time and brevity, I'm not showing all the algebra. You guys can do that. But I'm really just taking these expressions and subbing them in and doing some algebra and using some trig identities. So these first two terms turn into this. And then here, I'll expand this out, right? This is actually z squared minus 2z plus 1. So the 1's will cancel on either side, but we'll be left over with the z squared and the negative 2z. So the z squared is, in spherical, z is equal to rho cosine phi. So this will be rho squared cosine squared phi minus 2 rho cosine phi equals 0. Well, trig identity here, factor out the rho, this collapses down into a rho squared. So we should have rho squared minus 2 rho cosine phi equals 0. Solve here. And then we get rho equals 0 or rho equals 2 cosine phi. So the reason why, so rho equals 0, this is just this dot. A distance of 0 from the origin is the origin itself. So this is the equation of that surface, actually. So in spherical coordinates, this hemisphere that we have here is actually going to be, let's go ahead and just recap what we need here. This hemisphere here will be rho equals 2 cosine phi. So with that, we now know that we can say that rho is sandwiched above by that. What's rho sandwiched below by? Well, when you draw a ray through your region, it definitely hits this outer surface, the hemisphere, but it doesn't hit necessarily something on the inside. But this region, it does contain the origin, and in spherical coordinates, whenever your region does contain the origin, you know that rho here is going to be 0. So, 0. After that, what we want to go ahead and do here is think about phi. So to get phi, you can just project your region here. Imagine projecting it into the YZ plane. So if you project this region into the YZ plane, that's how we're going to find out what phi is. So if we actually sketch this in the YZ plane, we get basically this shape here. Now phi is the angle measured from the positive z-axis. So this angle here, that's what phi is. So down here, that's an angle phi. Up here, that's another phi. Phi is the angle, it's the deflection from the positive z-axis downward. So the question here is, what's our range for phi? Well, does our region touch the z-axis? Sure does. It's right in the middle. So we know phi starts off at 0. But then if we can imagine just increasing this angle gradually, at what point do we stop? Well, right there. This angle right here, whatever that angle is, that's the maximum value for phi. If you project this into the YZ plane, we see that this maximum angle comes from this equation. That's where it comes from. This maximum angle really doesn't have much to do with the sphere, with the hemisphere. It has to do with this cone. So the YZ plane, its equation is x equals 0. So if we project this into the YZ plane by setting x equal to 0, what do we get? Well, with x equals 0, this gives us z equals positive root y squared, which is the absolute value of y. So in the YZ plane, we get this. And what do we know about the absolute value? We know that the slope of the absolute value here is a slope of 1, a rise of 1 for each run of 1. This is a line with slope 1, and this is a line with slope negative 1. But in either way, this is a 45, 45, 90 triangle, which means that this angle here is pi over 4, which means that this angle here, which is what phi is, that also has to be pi over 4. So our maximum is pi over 4. Theta, we can find theta by taking our region here, our three-dimensional region, and projecting it down into the xy plane. Well, the widest this region is comes from this circle of intersection. So we could figure out what this circle is by taking the equation of the cone and intersecting it with the equation of the hemisphere that we did have in Cartesian. Skipping that step, just because for the sake of time, you will find that this circle actually is a circle of radius 1. So, the other thing is it's not terribly important to actually know what this equation is. What's really important here is to think about what the shape looks like. If you project this down, we get this full thing. Do you see how this region exists all the way around the z-axis? So this means theta definitely begins at 0 and extends all the way to 2 pi. So this is 0 to 2 pi. So in general, once you have those inequalities, these inequalities, we're always going to be doing the rho integral, phi integral, followed by the theta integral last. Always, always, always in this order. So we have our three inequalities. That gives us our three sets of bounds. And then we can go ahead and replace x, y, and z with what spherical coordinates has for x, y, and z. Lastly, our dv will be replaced with what dv is for spherical. Rho squared sine phi d rho d phi d theta. Lastly, some useful trigonometric identities. We, of course, have our standard Pythagorean identity, and then we have the two half-angle identities. One thing to point out here, these are, I guess this is bad formatting on my part, but these are not negative signs. These are like little bullet points. So this is not negative cosine squared. My apologies for that. It's following the same format as up there.